Capacitors connected in series behave contrary to how many people expect. Connecting capacitors in series results in smaller capacitance. In order to develop an intuition of why this occurs, let us suppose that we force a constant DC current through a capacitor for 10 seconds. Let's now force the exact same DC current through a capacitor with a larger capacitance. With a larger capacitance, the voltage increases more slowly, and at the end of the 10-second time period, the voltage will therefore be smaller than before. Let us now force the exact same DC current through 3 of these capacitors in series. At the end of the 10-second time period, each capacitor develops the same voltage drop as in the previous example. The total voltage drop across all 3 capacitors combined is the same as the voltage drop across the single capacitor with the smaller capacitance. Therefore, as far as the external world is concerned, multiple capacitors connected in series behave just like a single capacitor with a smaller capacitance.
So let's look at capacitor number 1. We talked about potential drop. So the plate, conductor plate, which is closest to the positive terminal of the battery, gets on the same potential V1. And please note the words potential versus potential difference. Now the second plate will have a lower potential V2 as mentioned there. So V1 minus V2 is the potential drop due to the first capacitor. It's as if we fixed a bulb out there. So as far as the first capacitor is concerned, Q equal to CV, so Q equal to C1 into V1 minus V2. Therefore, V1 minus V2 equal to Q by C1. And all these potential drops, as I said before, V1 minus V2, V2 minus V3, and so on, have to add up to the delta V, which is the potential difference of the battery itself. Can't be more or less than that. Now coming to the second capacitor, you can see that the second plate of the first capacitor and the first plate of the second capacitor are electrically connected by a wire. So the V2 repeats on capacitor number 2. Because V2 repeats, then the potential difference becomes V2 minus V3, because V3 has to be lower. And therefore V2 minus V3 equal to Q by C2. Now come to capacitor number 3. Now it is electrically connected to the capacitor number 2. I mean only 2 plates are connected. So the V3 potential repeats on the first plate of capacitor number 3. The second plate of capacitor number 3 has to be V0. Why? That's because it's connected electrically by a wire to the negative terminal of the battery, and therefore they can't be at different potentials. They have to be at the same potential. So V0 has to show up on that plate. Therefore V3 minus V0 is Q by C3. Now you add up all these individual voltage drops, the principle being that the total voltage drop must be same as the EMF of the battery. Therefore, when you do this equation and remembering to put V0 equal to 0 volts, you will get Q by C1 plus Q by C2 plus Q by C3 equal to V1. And then take out Q and you will get V1 by Q equal to 1 by C1 plus 1 by C2 plus 1 by C3. Now that is kind of a 1 by equivalent capacitance, which is C total. And therefore you will arrive at 1 by C total equal to 1 by C1 plus 1 by C2 plus 1 by C3.